today, good morning, and I think some of you are there in the yesterday meeting, right? This Teachers' Day meeting. I think nobody was there. Okay, let us start. So today we will start with electronic spectra in a bit explanative mode. So what we did last day, we did a little bit of this microstate, how to get the microstate, so that today we could avoid that part and we could directly tell that it is coming in that way, right? So that our discussion on electronic spectra will remain I mean this continuous. So the what is the point? So the first point is that, so what we did during the this ligand field splitting, so we have decided that you have shown that there are splitting and their ligand field actually there is a energy difference between the T2G and EG level. All these things we did, but the point is that, so from where do you get that values? I mean, do you have any idea that I mean it is only calculation? So there are people who do only calculation to check all these things, but definitely there must be some basis from where these parameters come. I mean, you have some idea that if you have ammonia and if you have, let's say, cyanide ion, then the crystal film splitting is different. So you know that right now from the orbital overlap and all these things, but there must be some supporting experimental thing that has given rise to this idea that there are the difference. So what is this what is this experimental thing? So the experimental thing is, one is the electronic spectra, second is the magnetism. So that actually give you idea that magnetism for a particular, let's say, M3 one particular M3 plus, so with one ligand it shows the paramagnetism, with another ligand with the same oxidation number it doesn't show the paramagnetism. So in from that you get the, so it is backwards. So you get that there in some cases there are this unpaired electron, and in some cases there is no unpaired electron. Similarly, if you have a particular M3 plus or 2 plus any cation, and you have, let's say, ammonia or cyanide, then you can see that for the same metal in the same oxidation number you may have different color, shades of color. Let's say one is orange is yellow and another is red. So you can understand that there is a difference of energy, and from that we can go back to the this repulsion. I mean the thing that there is a difference of energy between the states because of the presence of different ligand. So now, so last day what we did the microstate. We will not go to the elaborate this will not I shall not show you the again this 2 plus 2 minus test, all these things, but we will just go through this D2 system. And let me first uh, explain a little bit and then I shall, okay. Now, so today is day 14, right? Okay, so let us see that if you just go to the electronic spectra, so as I explained you, so what could be the thing? So first is a free ion. Free ion means we do not consider that there are electron repulsion within that. Let's say you have a M3 plus, and we are not considering that. Let's say we are taking the D system, let's say D2 system we are taking, and what is the repulsion? So it is T2G2 generally we look it like, or if we take D3, then we say T2G3. Now, we do not consider that there are any repulsion, so that we tell the free ion. Now you have the, let's say, not in that way. So you have the X, Y, Z axis. So if you have electron, let's say in these, so if you have electron, let's say here, and just for understanding, right? And you have dxz. So if this is dxz, so you have, what I have shown you is the dyz and dxz. So if there are electrons in there, so there must be an inter-electronic repulsion. So there is repulsion that we are not considering as free ion. So free ion, we are considering that there is no repulsion. Then you have inter-electronic repulsion. We got, I mean, if we go back to this, it happens. Now 3 is the system. Now you put in octahedral field. So these 3 things we need to consider when someone wants to say something. Please switch off this. There is some noise coming, right? So do you get any noise? Okay, now it is stopped. So these are the 3 things that we need to consider. Now let us take a real picture. So let's say you have a D3 ion. I'm taking, okay. So one thing I must tell you that today I am following mainly from Sievertskins, so that when you first time read, you can clearly understand this. I mean, this can be taught in different, uh, I mean, I can tell you the spectroscopic selection rule first or all these things, but I have followed this order because in different orders we can tell, but so that you can follow one textbook. So let's say you have a chromium NH3 whole 6, so D3, and you have T2G3 system. And if you go to the one electron goes to the excited state, then you can have T2G2 EG1. So practically, if we just take this energy excitation electron, then we must have one absorption maxima. But if we go to the real picture of this chromium NH3 whole 6 3 plus, then we see that this is very low intensity. So here it is magnified. So you see 1, 2, 3, and there is another thing called charge transfer. So if we go on understanding these, then maybe we will come to the terms that what is the difference between a free ion, and then what is the electronic repulsion, and then what is the transition. and this transition must follow some rules which are called selection rules. So first is that this repulsion thing we will read, and then we will go to the transition, and for this transition you have some selection rule. Selection rule, right? And this selection rule and the intensity actually depends on, we will come to this in detail. So intensity will come to this, depends on whether it is allowed or forbidden. So you can see that here it is very low intensity, so it is forbidden, and these are allowed transitions. Now, and this charge transfer will come separately to the charge transfer. This is not within the D system. These again take the, the third one, the transition between the D electron, D orbitals, and then it goes to the mixing of the metal and ligand. When you have seen the this bonding, then we have taken account the ligand is orbital overlap is there, and ligand this is a position and all these things. But here when we are taking the electronic spectra and when the orbital overlap taken place and all these things, then the system does not know what is the this d orbital and what is this. So it knows that where it will go according to the energy. And in some cases, it depending on the energy of the orbital. In the molecular orbital, as I told you, that molecular orbital, even if we are theoretically say that the molecular orbital does not have any particular name like metal orbital, we have seen that the bonding orbitals that are very close to ligand orbitals, and that is of ligand character, and the metal, the antibonding orbitals that are with metal character. And in such cases, if the electron from this ligand orbital goes to not this T2GG, not this d orbital only, but from this bonding orbital to any of the antibonding orbital or ligand close orbital to any metal close orbital, then this is called charge transfer. This is not DD transition. So there will be two type of thing. One is DD transition, and another is either ligand to metal. So it is ligand to metal means, or by molecular orbital close to ligand to molecular orbital close to metal, or metal to ligand charge transfer. This is called charge transfer, to differentiate between these two. Here. Now, let me put one. Okay, let me put it here. Now, if you have a D2 system, I am not drawing it by myself. So last day you know how to draw it. So it would be like this. So my request is that as you learned it last day, so you please, once the class is over, you please check that if you have disagree in any cases, then please let me know, and then I shall explain. But this is the way we can write it. And here two things we have taken. One is Pauli's exclusion principle, as I told you last day, and second is the Hund's rule. So after getting the permission generally, so this is the D2 system, and we get the 45 total microstates, and this is 10 factorial and 10 minus n factorial, and then n factorial. N is equal to the number. So how it is coming, and what microstates go to where in number of free electrons. Okay. Now, as now, as I shown you, so let us build from. So ml is equal to L12 plus 1, right? And ms is equal to 2s plus 1. Now, L can have value L1 plus L2. Then you have L1 minus L2. Sorry. Now, if you have L is equal to 4, so if you have L is equal to 4, then if you have ml is equal to 2 into 4 plus 1 is equal to 9. And then if I take ms value, so ms value, if I take ms value is 0, because you can draw it. I mean, if you want, you can draw it. So it is the plus 4. I mean, let me start with plus 4, and then this is the 9, and then you have this 9. So if L is equal to 4, then you remember that L 0, 1, 2, 3, 4. What are the value? Is S, P, D, F, G. So it will have the G term, and S is equal to 0. So 2S plus 1 is equal to 1. So this is the 1G term. 1G term is equal to L is equal to plus 4, and I mean 4 is the term. And as L is equal to 4, you have these terms, I mean these different terms. So you can have like you can have this value, and L plus 1, L plus 1, L plus L1 plus L2, L1 plus L2 minus 1. In that way, you will have all terms. From here, you will have total of 9 terms. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 terms here. So you can just take like this blue one is the total microstate. So this is the state. This is the state. And under this there will be 9 microstates. So you can draw it. I mean, you can draw it and take the idea from this 3p system, and then you will have the other value. I mean, next is the L is equal to 3. So you will have F. And if L is equal to 3, you will see that there are ms value is equal to 1, and then you have the term 3f. Now if you have 3f, so 2l is 2 into 3 plus 1, so it is 7, and then you have s is equal to ms 1, So 2s plus 1 is equal to 3. So here you would have 9 into 1 microstate, and here you will take 7 into 3 microstate. So here you can now, here you can do it like that. You just cross one of these. That you have to take now with 21. You can see this is the 21. The red one is the 21 microstate that span between -3 to +3, or you can say +3 to -3. And in that way, you will have total of 45 microstates, and you can have one is 3f term, 1g term, 3p term, 1d term, and 1s term. So this is the system for D2, and for D3 again you will have the terms. Now try to understand that we are not going to understand the calculation over here. So these are not, we will not do all these things together. We can just say that how many microstates are there like this, and then we will learn that what is happening. So if there is a D2 system, you can learn, or in the question paper it will be given that what are the terms. Only one thing you can, you may have to calculate that which one is the ground term. So now the point is that, let me explain first and then I shall tell that theoretically, when we say which one is the ground term, so the ground term we consider from the free ion. So from the first was the free ion, and then we have this repulsion, electronic repulsion. So from this we take one of them is the ground state, and we have seen that this ground state, from the free ion term, there is a energy uh, consequence, that if we consider all this Pauli's exclusion along with the Hund's, all the both the rules of Hund's, then there is a distribution according to this. As I told you, the highest L value and the highest S value will have the ground term. But what we have seen that, and what the scientists have seen that, uh, the the ground term remains the same, but the other terms does not follow the way that we are expected exactly. If we just take this, we are taking that these terms we are taking, and let's say the ground term becomes 3f. Let me consider. So ground term is 3f. So once the 3f is excluded, we have other four terms. Then we can apply the same rule, the greatest multiplicity and then the greatest L value. But according to, we can keep the values. But what we have seen that this doesn't follow the rule, and the rule is a little bit different when we just take the interionic repulsions. And what happens when the ligand comes, this again becomes very different from the term that we consider from the free ion along with the this ligand field. So this is the actually the arising from configuration from the this free ions. So is it clear? I mean, I think it is clear till now. Okay, so if I go to this, then the terms come as 3p.
Hello, ma'am.
Yes.
Ma'am, actually, what kind of question which we can expect from the microstate part?
So microstate part one, the calculation of microstate, you can expect only one question, that is what is the ground term.
Is the ground, we have to derive the term and symbol for the ground state.
Ground state only, right? Or number two is very small, that how many microstates are there. So everything is the formula. Okay. So what I am explaining now, that you have to understand to for the next part, right?
Okay.
Okay, so this is the microstate. So the free ion, nothing happens in the free ion, as you understand, right? So everything happens when there are ligand.
Okay.
Right. I mean, even if you are taking it in solvent, so it is in water. So chromium, if you just state that it is aqueous solution, then what you are considering? You are considering chromium H2 whole 6. So let me go a little, and then I shall explain. And I shall go a little bit fast, so that we can keep at least 3 hour discussion on the different type of questions, because the spectra, what you understand from the theory, is much more important is that what you understand from the examples, right? So I may go a little bit first, but let me uh, finish it so that I can go to the example. So this is the relative energy. If we just do the relative energy from the free term, I forgot to keep it here. So this is the term, that is the free ion, but actually what we see, 3f, this is the 1d, this is the value. So if we just take the this is the inter repulsion. So how do you define the repulsion? So I'm every time I am telling the repulsion, what does it mean? So what does it mean? See, I mean, you may not get it in book, and I am just trying to explain it. Let's say so if you have, so I told you, sorry, I told you that, I mean, if you have this repulsion, from this repulsion, actually this term changes. This term change is for the inter-electronic repulsion within the free ion. So one thing is the free ion we were considering without any repulsion. Free ion means without any repulsion. Second thing, we are considering here the inter-electronic repulsion, right? Okay, now if we just see that how does it, let me, E1 is this I told you that it happens. So how does it happen? Let me see this value. I have to little see from somewhere. So 114b plus 7c, and then any book you will get E1g. So see that A value, I shall explain what is A, what is B, but you see that A value will remain the same. 4b plus 2c E1d is equal to A plus 3b plus 2c E3p A plus 7b E3f A minus 8b, right? So these are the values. Now this, what does this mean? So these are called Raka parameter. This is important. So there are too many important things than calculation of microstate. So microstate is very easy. It is just the foundation. So Raka parameter. These are called Raka parameters. Now what is A? If I see that A, then A is the average. You'll get in any book average of total electronic repulsion. So as from the value as A is there, so generally what it does, we just not neglect, but we do not consider the A, because it is the value of B and C that actually differs. So we just take the value of A in all the calculation and then we start, right? And the B and C is the repulsion for specific for this, specific for the state. Like what I told you, that this is the state, right? And under this there were microstates. So state means you have one orbital angular momentum, you have spin angular momentum. So there are like, maybe I can show you that one thing can be like this, another thing can be like this for a particular state to keep the S value highest, S is equal to 0. But the repulsion between these two, this one and this one are not the same. So all this specific repulsion thing will be taken care by B and C. So let us explain how we are taking this. And for these things, always Hund rules, for this particular case, the energy order, this is the real, and the energy order always does not follow the Hund's rule. Energy, to write. Energy order does not follow Ohm's rule. So what is the reason? Let me explain a little and then. So I mean, it's not that I can explain it totally, but just trying. Another thing I have to tell, I forgot. I shall tell you. So let's say you have, I mean, why this? Now recall this one. That there are different transitions, right? Theoretically, T2G1, T2G3 to T2G1, this is the excited state and this is the ground state, but there are two different transitions. So let us consider, let's say you have a DZ2 orbital, DZ2, which is a EZ orbital, right? And you have electron density electron density XYZ. So electron density in X and Y. So your change is dxy to dz. Now the electron density that this dxy have, no component in dz2. So the relocation, I mean, it is physically, you think that the electron density was in this direction. So there is no component along z axis, and then it is going to the z axis to dz2 component. So it is a complete relocation. so the energy required is high. But if you have a energy at dyz or dxz, then you have a component along the z-axis, and that goes to dz2. And and if you think of opposite, these one when going to the dx2 y2, it's have the component x or y component along dx2 y2 orbital, and this one also have this x2 xy component, and but there will be also be a little difference. And what happens, the spectra, now you try to understand the spectra, may be a spectra which looks like just this, may be a combination of is very minimal this. So if the energy difference is very small, then it comes as a single spectra. Until and unless the energy difference is a little bit, it doesn't show that, that is not reflected. So with all these things and this uh, selection rule we will take care of, then you have these spectra. So this is the spectra apart from the charge transfer. Okay, now, okay, another one thing I forgot. Let me just tell you one thing. Okay, I am just writing. I shall not explain it today. So there are points when you have, this is a little bit different. When you have C greater than 5B, you have, I shall not, you just remind me next day that I have not explained it, because I just want to finish this one, and this will help you to correlate, and next day if anything is required I shall again. And this is the C4B. So there are different situation arises, and I shall explain it next day. Let me move here. Okay. So what happens? So now we have taken free ion and we have taken the inter-electronic repulsion in this free ion. Next, what we will do? We are introducing the ligand. So once we are introducing the ligand, then you have the octahedral geometry, octahedral symmetry. Now you have, so we have covered the free ion. So there is a energy order in a free ion, and then we have taken inter-electron repulsion. There is one order, and now we are putting the ligand, and this ligand you have octahedral symmetry, the simple symmetry we have. So once we put it in the symmetry, then it is in the symmetrical element. So when it is just like the thing, you have to remember that A is totally symmetric and it has 1G symmetry, P number of states 3, and then you have T1G, D is 5, and it is in the T2G. So now if I draw it, now if I draw a spectra, then how does it look like? Let's say we are taking a D term, and in absence of, this is 0, and this is the presence of, this is the, if we put ligand strength, like we are going from weak field to strong field. Then if it is a point, let's say 1D, and then it breaks into like this. So EG and E2G, and depending on the ligand field, these value changes. This is very simple thing, because here when we are drawing this, we are not taking care of, I mean, exactly we are not taking care of Raka parameter, we come, we not taking, we are taking, but it is not showing the energy. So if we are telling this is energy, then we are, if I just say energy, we are not taking Raka parameter. We have to give the x and y axis. We have to change accordingly to take care of the Raka parameters. Here, I just wanted to make it clear. So if we just increase, and this is the del zero value, and what is the ligand that depends on this ligand, del zero value changes, right? Next, if instead of energy, we just put the, here there exactly one term is there, I shall come. If we just put it like that, then we can see that these values, the states again, when different states in presence of the ligand, they again change the place. Like for one example, that these two states, when we have just taken the inter-electronic repulsion, then these two states have this value. But I mean, here also, even if you just let's say you just put it like this, up to this ligand field strength is not, then also all these three will go be there. So the transition, you can say that it is going like this. But once you have strong field, you see that the strong field, all this thing changes. So depending on the ligand field, the arrow will change, that now the energy order becomes totally different. So if you just want to go from here to here, things will change. I mean, this all depends on the ligand field. And what is the time? Little bit time is there. So this is called the, sorry. So this is called the Tanabe Sugano diagram. And don't expect that someone will tell you to form the Tanabe Sugano diagram. No, nobody will tell you to draw a Tanabe Sugano diagram. Nobody will tell you to say that what is the energy order of a Tanabe Sugano. No. So what could be the question, that if it will be given that this is the Tanabe Sugano diagram of a D2 system, and if you know, I mean, before, if you learn to read the Tanabe Sugano diagram, you will have the idea of the selection rules. There are selection rules for spin allowed transition. This is Laporte forbidden, and Laporte allowed, different type of transition rule that will consider the spin multiplicity, that will consider the orbital angular momentum, that will consider the crossing of the states. I mean, the crossing of different states are not allowed. Like 1T1 will never cross with 1T1, like a different type, and they will repel. That why that will happen, that I shall explain. But you don't have to remember. You will understand. Yes, why this? You see that if you just see that this is okay, 3T2 and 3T1. So these three values, spin multiplicity is the same, and they are not crossing. So A1 not crossing, and even they are not crossing, at some point of time they are repulsive. So this is not straight line. Sorry, this is not, you can say this is the not the straight line. This is also repulsion is taking place. So why it is happening, that will be explained, but not that. So what you have to do, let's say you have this structure, and it is given that this is the D2 system, and then you will be asked that let's say this is chromium cyanide things, and you know that cyanide is very high, I mean, strong field, then you will ask to give that what transition do you expect from that. Or if you have, let's say it is given that what is the transition. Transition is given, and it is given that what is the energy difference, and everything will be given. You have to just understand to read the Tanabe-Sugano diagram, and you will find. We'll do it, so don't worry. Then let me know from that part what you did not understand, and then I can go a little bit more. It is 11:50, so please let me know if I have to from this part, if I have to say anything. Or I shall write the points. Please let me know. Is it clear? Okay. So for the next class, I shall not tell much thing, even if I can right now. So the thing is that how can we electronic spectra summarize? So next day we can start reading the Tanabe-Sugano. So the first thing is the free ion. Second thing is the inter-electronic repulsion. Third thing is the presence of ligand in specific field. So specific field means octahedral, tetrahedral, square planar. Definitely, the Tanabe-Sugano diagram for a particular thing will change in some other field. Then presence of weak field ligand, strong field ligand, and then summing up both the ligands is the Tanabe-Sugano. Summing up both the things. Tanabe-Sugano take care of all these things. These plus these, all these things is taken care by Tanabe-Sugano diagram. And now what are the rule for transition? This will next day. What is the selection rule? So there will be some allowed transition and some forbidden transition. And then we have, okay, is the charge transfer spectra. And for charge transfer, again spectra, again we will go back to MO of octahedral, tetrahedral, because then we have to look at the field orbital and empty orbital. And this, then some forbidden becomes allowed by some relaxation, that we'll read it in a little bit. Relaxation for transition. And this G value, G transition, G to U, all these things we will learn. Okay, thank you. And